Sorry, I'm having a bit of issues opening up the file. Okay. Okay. Mm, yeah. Sorry for the delay. Let's see. Okay. So welcome to again machine learning for material sciences. We started basically just a quick recap. So we started with AI again, machine learning. We supervised, unsupervised, gradient descent, and then feature engineering ensemble. And so we covered a bunch of machine learning algorithms, which basically are really good, of course. But as we understand, we have moved on to a little bit more advanced concept, let's say, and which has been driving machine learning for past, let's say, 15 years or so. Yeah. Specifically because of both of data as well as GPU compute that you have. Yes. And we talked about one of the fundamental settings here. Basically, we wanted to do neural networks. And to start with neural networks, the starting point was basically a perceptron. Yes. So then we started with comparing like how biological neurons and artificial neurons compare against each other. We gave some historical context, some mathematical foundation. Then we defined what does a perceptron mean. Then we specifically discussed a bunch about activation functions, sigmoid, hyperbolic, tanh, and then ReLU. We discussed the problems with each of those activation functions, but finally we ended up with okay, ReLU works really fine, uh, even though it still does not solve all the problems. And then there was a convergence theorem on, sorry, convergence theorem on like perceptron training algorithm. So I told you like if you train your algorithm through these 1, 2, 3 steps and your data is linearly separable, you have this convergence. That means it will take at most these many mistakes to converge or these many iterations to converge. Yeah. And then we landed up with this particular slide. I told you that we'll start from here. The major idea behind this particular slide is just to say, sorry, yeah, uh, yeah. That means if the like problem is linearly separable, we don't have an issue. But if you remember the first paper that like first work that came out that they will okay, you can use perceptron or let's say artificial neurons to solve all sorts of logical problems. Then there was another paper refuting this, that there is okay, here goes a very simple logic function called XOR, and I proved that basically a single perceptron will unable to be solve it, right? So the idea is basically XOR, if you know, it's basically like, let's say, how do I say? This is the table for XOR. So if it's 0, 0, you get 0, and if it is 1, 1, you get 0. Any of them is 1, at least one of them is 1, or they are not matching, then the output is 1. So this is your XOR. Yes. And the idea is basically no single line will be able to separate the XOR classes. Yeah. And sorry. Yeah. Now I will show you the 2D plot also. It will make more sense there once we go. So, but let's say we want to, let's say, prove first why a linear separator cannot do this. You can assume that there is a line that basically separates them linearly, and so that would mean that there exists a set of W and let's say W2, W1 and W2 are a set of Ws and the bias B that walks set. So you have a perceptron, you have a W1, W2 that is coming in. Yes. Now all the four conditions we have to write. All the four conditions are basically derived from the XOR itself. So that means whenever there is a 0 and 0, output should be 0. And whenever 0 or 1, output should be 1. So W2 plus B, because the first one, everything is 0. So W1 plus W2, they don't matter, because W1 multiplied by 0 is 0, W2 multiplied by 0 is 0 again. So whenever it is 0 comma 1, that means W2 plus B is greater than 0, and then W1 plus B also has to be greater than 0. But then you have the opposite condition also, like wherever 1 comma 1 is basically 0, you have W1 plus W2 plus B is less than 0. Now, the point is, if you look at this, if you just take the conditions 2 and 3, you will see that W1, W2, W1 and comma W2 has to be greater than minus B. Yeah, both of them. And also, of course, like greater than 0. Uh, but the condition 4 specifically requires that adding both of them has to be less than minus B, right? So then we'll end up with basically a contradiction, right? So that's the proof basically. So basically an XOR cannot be, there does not exist like a linear separator for XOR, and perceptron at best can do linear separation, and that is that is why XOR as a very simple logical function does not work. Okay. So this was a repeat of the previous class. I will just show you the slides now and then we'll move. I'll show you the code, how it looks, just to have a little bit more clarity. Let it go. Okay. Sure. Okay. I hope this is visible. The exact code is not super essential. Let me see if I can zoom. Okay. This particular notebook is already shared on the class website. You can take a look. So this first figure is on basically what are the activation functions, how do they look like. If you remember, the primary activation function was anything greater than 0 will be 1, anything less than equal to 0 has to be 0. Uh, Hence, we have this step function, and the step function is definitely non-differentiable at z equal to 0. Yeah. And then we had the sigmoid function, 1 by 1 plus e to the power minus z. So that's a sigmoid function, and the corresponding derivative is just the below. Yeah. And similarly, we have tan h function, and the derivative is again below. And the last one is basically ReLU. ReLU looks like that. So everything that is less than 0 gets the value of 0. Everything that is positive gets the value of positive. Yes. And I told you like sigmoid and tan h, like sigmoid has an issue that there is no negative. So that means the gradient does not flow. Matlab, on the other direction, uh, it's not a symmetric optimization. That's what. And also the diminishing gradient, because if you look at this, anything that is closer to, let's say, anything that goes beyond, let's say, values of, let's say, 4 or minus 4 here, it's very close to 0. Yeah. Uh, and then you have the tan h function, which basically solves half the problem. Yeah. Uh, that is, it is at least symmetric. That means you get both positive as well as negative values. So it is at least symmetric. Yeah. And but it still has the diminishing gradient problem. If you look at this, then minus 2 to 2, then beyond that, everything is squeezed to 1 or squeezed to minus 1. Yeah. And you can look at the derivative. The derivative also, like basically, if you look at derivative, minus 2 to 2, beyond that is basically 0. Yeah. But it's not exact 0, but very close to 0. And if you look at ReLU, ReLU is much nicer in the terms, at least positives positive area does not have anything. It's straightforward calculation of 1, anything negative that is 0. Of course, it is non-differentiable at z equal to 0, but we can take the value as 0. Like we can make it simplify and make it as 0. And it solves the problem of, let's say, vanishing gradient. Yeah. It still does not solve the problem of how do I say symmetric. There are other things that come into play. There is one more I told you, like something called a leaky ReLU that can be used to solve that issue. Now perceptron is there, and so if you have linearly separable data, there you can definitely find a perceptron. It will take r square minus gamma square, a number of let's say maximum that many number of iterations to find that particular line. Yes, it's very similar to other algorithms that we have studied before. But you see the classes are there. It's like a linear line is there which can separate. Uh, so we have that ready. Yeah. And if you want to visualize, for example, like if you look at epoch, I hope I told you about the epoch and all this. So epoch is basically says iterations is every iteration is where you update the parameters of the model. That means if the weight and the bias you update, then that becomes an iteration. And and the batch is basically how many data points you look at so that you iterate, like how many data points you look at before you iterate once. That is your batch. Epoch is like basically you the moment you look at all the data points, at least the first time you complete looking at all the data points, that is one epoch. Second epoch looks at the same data points again. So that's what it says. So at 0th epoch, this is the number of misclassifications that are happening. That means the first line that was random, that mean did. After I look at every data point, and every data point I did, like once I looked at a data point, I updated my weights and bias. So on and so forth. By the time I reached at the end of that epoch I have looked at, so it has become very less. I did only, let's say, one misclassification. And if I look at the epochs again, like one more round of data point, then it solves. Yes. And similarly, if you can see, like the first epoch, basically the bias got fixed, and the second epoch, the bias is not changing. The first epoch itself bias got fixed. And similarly, the weight 2 got fixed, weight 1 also around and about got fixed. Yes. Slight changes are there. It's not visible to eye because anyways it was making only one mistake, so it was just minor change. Yeah. And the last one is basically the XOR problem. So XOR problem is here. So basically you can see like there is a whenever it is 0 comma 0, it is 0 left bottom, and the right top is basically 1 comma 1, and 0 comma 1 is something is 1, and 0 1 comma 0 is 0. So red color tells you that it is 1, blue color tells you that it is 0. So if you see, there does not exist a line which can do it. Fine. But perceptron can only do linear separation, let's say. And so then you end up with this basically. So perceptron became an algorithm where you have these issues. Yeah. Okay. Now we will, I hope, this is anyway shared. The code is important, of course, but I think like that you can check after the class. I will now move on to the next one. Hmm. Sorry. Okay. Yeah. I hope everybody is here. Fine. So the next one is basically neural networks class, basically the second class of it. So here we are trying to see, okay, we understood uh, neurons, like from biological neurons, we can get inspired and do singular neuron perceptrons. But also we understand like brain is not a single perceptron, right? Single neuron. So it combines like trillions of neurons. So similarly, like we will look at how multi-layer perceptron we can build, which includes many artificial neurons, and together how it can solve problems that the single perceptron cannot solve. Yes. And then, of course, because we have multi-layer perceptron, we'll also take a look at the backpropagation theory. Yeah. So that's the idea of this class. And okay, sorry, yeah. Uh, okay, so here there are a few confessions, let's say. So some of the theory behind this is relatively maths heavy. I will cover some part of it. I will first glide over it. If there is a requirement of covering this one, we will have to take another class to do so. But today I want to just to make sure that you understand most of the parts, and then at least on the like from a larger perspective, you understand how these things work. Yeah. So at least you can answer question where this will work and where this will not work. Yes. So specifically why we require multi-layer of perceptron. Yeah. So the next is, so the first thing that we start with is the problem that we had with single layer perceptron. We understand that uh, whenever we have an XOR-like problem, wherever there is no single hyperplane that can exist to solve the problem, let's say, it's simply not like single perceptron won't work. Yeah. So now what is the answer? So the solution to this is basically very simple. Instead of one perceptron, like probably use multiple layers. Yeah. So if you use multiple layers, that can create non-decision linear boundaries. Yeah. So because a single perceptron creates one straight line, then if we combine multiple decision boundaries, they can create non-linear regions. I hope you are able to. So one line we have like one perceptron can create, let's say one line, right? But we can use many lines, straight such lines using multiple perceptrons that can eventually it will be linear cut by every neuron, but that eventually if we combine across, so it becomes like a non-linear, like a curve would be like a, how do I say, the way you do like piecewise linear operations. Yes, fine. And so what we have here, like input layer will have features and the hidden layers will have intermediate representations. Yes, so that means the somehow the features go in, there are intermediate representations that are getting formed, and the output layer will give you the final presentations, final predictions. Yeah. I'll show you the figure. Okay, fine. And sorry, give me like one. Okay, I'll cover this one and then I will start sharing the other one so that it makes sense. Maybe. Hmm. So that means the solution is to use hidden layers. So the hidden layer basically creates two half planes. Let's say for one of the example is, let's say we take a two-layer MLP. So the hidden layer will create two half planes, and the output layer basically combines this half planes, and eventually we get a nonlinear decision boundary. Yeah. And and is also backed by a theorem that you, if you can increase the number of layers, eventually you will be able to approximate anything, any function. Okay. That's why I told like much like neural networks do not have any bias towards, because they're like, very low bias. So because they can approximate all the functions possible, linear, non-linear. Yeah. Before we jump on, I just wanted to show you the figures. How does it look like? Okay, sorry. Okay, I hope you can see the figure. Fine. So here, what we have is basically on the right hand side, I have your like the XOR problem itself, and the left hand side is the multi-layer perceptron here. So if you look at the right hand side, this is your basically the XOR problem. I told you the same thing, like the triangles are basically, let's say the output is 1, the red are basically the output is 0. That's why they are so. And if you look at a single perceptron, it is definitely not linearly separable. So the MLP solution is if we can have a nonlinear boundary. It does not generate that fancy circle, but we'll talk about that. So the way multi-layer perceptron looks like is on the left hand side. What you have is basically, you understand the single perceptron looks like. A single perceptron is just the one blue thing. Yes, it takes an input, combines with W1x and W2, W1x1, W2x2 plus the bias, and then there is a function on top of it. That function is an activation function. That could be a sigmoid, that could be a tan H, that could be a ReLU. Yes, that one single perceptron is here a particular node. Yes, a node is basically a circle here. So what we do is we combine multiple nodes, like as in if you see, look at this, the input is basically x1, x2, and x3, x4. It goes as input to multiple neurons, let's say each of the neurons, and then from each of the neurons, the same information passes through three intermediate layers. Yes, so this is basically the input layer X is sending information to H3, H2, and H1, and anything that remains in between, that is called a hidden layer, and everything that gathers the information from the input is called an input layer. Yes, and every node that connects to another node here, like on, let's say bottom blue one connects to the top one, there is an edge that passes by. All these are basically the weights. Yes, by some weight, this is equivalent to the perceptron that the input is coming, and here you can see the H3 is receiving inputs from X4, X3, X2, and X1, and all these edges basically they represent the weight of it. So it is basically W1x1, W2x2, W3x3, W4x4. Yes, because these are the weights of the first layer, everything that has been divided by the layer is called like the first layer. The the subscript, like the way to write it is like W, and then if you see it's like superscript 1 in brackets. That means all the weights belong to the layer 1 weights. And once we have this information for H3, because H3 will get input as W1x1, W2x2 plus W3x3 plus W4x4 plus the bias, we add them all out together. Then we apply a like a activation function, let's say ReLU here, and then that output is now ready from to go from H3. And similarly, it happens with H2. Similarly, happens with H1. And all these three outputs again go and join with Y here. Yeah. So H3, H2, and H1, they will also get like the second layer weights. So it will be like W1, like superscript 2, and then W2 superscript 2, W3 superscript 3. They will take the inputs that are coming from H3, H2, and H1. It will be combined plus the bias. Then it will, you will multiply and like you will apply an activation function, let's say anything ReLU, and then there will be an output function. Yes. So this is how a multi-layer perceptron looks like, and this is the XOR problem that we are trying to solve. Let me go. Okay. Okay. We are back, and if you can imagine with like XOR with like to this, we'll just cover initially briefly. Like there is something called a universal approximation theorem. What it says is basically a feed-forward network with a single hidden layer. Yes, there is only one hidden layer. You can have many hidden layers, but the idea is a feed-forward network with a single hidden layer with a finite number of neurons. But the finite is basically, it can be too large also, can approximate any continuous function. Okay, on a compact subset of r to the power n and to arbitrary accuracy. Fine. Uh, so what does it say? Like solution can in existence guarantee is there. Solution exists for any continuous function. Not constructive. Does only problem is basically it does not tell how to find the solution. Like how many number of neurons are required is also very tricky. And even if you set the finite number of neurons, you might end up not knowing what should be the value of the weights. Yes. And practical limitations, as it says, like may require exponentially many neurons, which is eventually correct, right? To universally approximate to a very particular accuracy, very complex function, the hidden layer will have almost way too many neurons. Yes. But anyway, but such a theorem does exist, and because such a theorem does exist, it makes MLPs very powerful. That means if you did not have any, how do I say, restrictions on the number of neurons you can have in the first layer, let's say first only the only hidden layer, then you can technically approximate any function, right? And all we know that you can basically, all we are trying to do is we are trying to find a function that maps x with y. Yes, and technically it's a function, and we have a proof that MLP can approximate that function. Yes. But like the truth is of course like very different from theoretical answer here. The point is like it will depend very much on the learning algorithm that we have, because MLP, they look very similar, as in the term MLP is very generic. The architecture itself can matter. How you train the multi-layer perceptron, that matters, and how is the depth also can matter. Yes. So the last point is basically deep networks can be more efficient than the wide. So wide is basically if you have, I told you the perceptron layer. So input has few neurons, hidden has few neurons, and the output has, let's say, one or two neurons. And the universal approximation theorem says even if you just have one hidden layer and many neurons in this hidden layer itself, you can have approximately like you can converge. But the idea is like this can require many such neurons. So what people do in practice is basically they instead of having wide networks, they have deep networks. That means they, instead of having just one layer, they have many layers here instead of having one layer with many neurons. Okay. So currently as it stays, so instead of doing one hidden layer with many neurons, exponentially high neurons, typically what we end up with is basically deep networks. And that has been shown to work nicely. Like last 15 years have shown, okay, deep networks works nice. Yeah. And so then we look at basically forward propagation. Forward propagation, I will just go back, is the one that I basically told you on the diagram itself. Yes. But it just says it in a little bit different way, through proper math formulation. So you have the input. Okay. Let's say the values exist. Okay. And a AL is basically activations at the layer L, and A0 is the zeroth layer, which will not have any activations because it's the input. And then WL is the weight matrix. At that particular weight matrix, we tell because it's a combination of that weight. I hope I covered the math basics where I told you that why that is a weight matrix, because it is a collection of all the W's, and but each W has multiple dimensions. Yes. So that's why it ends up being called a weight matrix. And L is basically, it's a weight matrix from W1 basically tells from 0 to 1 what are the weight. Yes. BL will basically tell the bias vector at the layer L, and then sigma is basically the activation function, sigmoid, tan H, and ReLU. Yes. And pre-activation is basically says Z is equal to WA plus B. That's you can do it if you don't have activation. So that means you can apply AL is basically same as sigma of ZL. Yeah. whatever is inside that sigma function is the z, that is the pre-activation. So here if you look at, so the equations are very simple. So it is basically w multiplied by a, basically dot product a plus b. Yeah. So all this is done, and then there is a non-linearity applied, that is the sigma is a non-linearity. Yeah. And then that goes to the al. So a0 becomes a1 after these operations. This is the layer, first layer operation. Yes. Then if I repeat it again, A1 will become A2 with again some operations, like all these operations, and so on and so forth. This particular operations can be repeated as many layers as you want. Yes, fine. Uh, Two-layer example, I showed you on that figure, we discussed through the figure, but this is again like more going through the formulations itself. How do we have? So layer 1 is basically the hidden. So Z1 will be W1X plus B1, and then A1 will be sigma of Z1. And layer 2's output will be Z2 will be W2 A1 and then plus B2, and then A2 will be sigma of Z2, and which one is basically equivalent to the Y that we have. And if you look at this, this is called a detailed computation chain. This one also called a computational graph. Yes, if you can make a graph out of this. Yeah. And then finally, this is what the total forward pass looks like. Forward pass is basically from the input to the output, how it progresses. Fine, that's all. Uh, so Y will be basically whatever this one is just has been combined. Yes. Like nonlinearity applied once, W2 multiplied by nonlinearity applied again, W1X plus B, then plus B2. Okay. So the few things that you have to be careful that will come with practice is basically the dimensions. The major errors while you are trying to implement a neural network, if you're starting off with it, the first error might you get is probably like the dimensions mismatch error. Yeah. So somehow you probably include a matrix where dimension is not matching, but you are doing a multiplication, there's some issue, right? So, but if you keep track of the dimensions of the matrix, this will solve. But it's also not that difficult. If you use libraries like TensorFlow or like let's say PyTorch, they sometimes they explicitly ask you this, but most of the dimension problems will be resolved. I will not say there will be still dimensional issue, but it's very intuitive. You can like easily write the dimensions, exact dimensions as you want, and the multiplications will happen. Yeah? So basically input dimensions NL minus 1, that is NL, and weight matrix is WL, and then bias vector. So you find out what dimensions they are all belonging to. Yeah. So in a 3-to-1 network, so where 3 input neurons, 2 hidden neurons, and 1 output, you will have input X, like R3. W1 will be because it is going 2, and then R2 cross 3, and then W2 will be like 1 cross 2, and eventually output 1 is of I1. Yeah, fine. And the other is basically MSC are there, loss functions are there. What you have is we have covered this anyways. So mean squared error, and the advantage is of course it's like convex for linear models. It's smooth everywhere. It has large penalty for large errors, and its derivative is also simple. The second loss function, we have not covered it directly, but we have covered it in some way. If you look at this one, this is exactly like a maximum log likely or minimum log likelihood error. Yes. So it's it's also called a cross entropy loss. Yes. So if you look at for binary classification, it's straightforward, negative of y log y, and then 1 minus y log 1 minus y, and then wherever there is y cap, it is like predicted value. Yeah. And this we have seen before, so I'm not like going into depth here. Multi-class classification. So the previous equation works because we have only 2 classes. If we have more than 1 classes, we have to do the below equation. It's almost similarly the same, but yeah, fine. And Sorry. Okay. Now, what are the benefits of a cross entropy loss? We have seen in the logistic regression also for the log likelihood error. Similarly, because output stays between 0 and 1, we can have probabilistic interpretation. It's also convex in parameters, and the derivative is also okay. Matlab, it's easy to calculate, it's not super bad. Yeah? The advantage is, of course, this has a faster convergence than MSC. Anybody can guess, like in the participants, why it should be better for classification as compared to, let's say, MSC? If you're thinking, you can write in the chat. By the time probably I complete other topics, maybe like while you're thinking, also you can type. I'll give it some time though. Maybe towards the end a little bit. Yeah. So now what happens is I will just go to the, I'll have to share another thing. Give me like 1 minute. Okay. Okay. I'll just reshare on the files. Have to share and the picture with you. Okay. Fine. I hope you can see this. So it's the same figure on the left hand side that we have, like it's a multi-layer perceptron. Fine. And then on the right hand side is the forward and backward flow. Yes. So now what we have is forward flow is very simple. So you start with the input layers X, let's say you move to the hidden layers A1, then A2 and A3 as many number of layers you have, and finally A2 or A3, wherever you stop, that becomes your Y. Yes. And you multiply weights and add biases in the middle and apply nonlinearity for every layer. Yes. Now the problem is not the problem. Like the next question to ask is basically how do we find the value of weights? Yes. So that is why, and that's the reason why we have why I discuss the loss. Yes. So remember every other algorithm that we talked before, they also learned because of the loss function, right? So depending on how far are you from the actual prediction, you calculate the gradient. Yes. Based on the gradient, you basically are asking it to move left or right. Yes. Like the on the axis or the value. Yeah. Less or more. So here the point is like if you look at the number of edges on the left hand side and the middle number of edges, you have a bunch of weights to do. So what happens is the forward pass, if you can look at, is like the blue and then all the blue layers that goes through. So if you can assume that let's say each layer has only one node, then what happens? Yes. So right hand side is basically each layer has only one node. So we have input layer X, we have one hidden one, hidden two, and then output. Yes. Oh, once we go through the forward pass, we take in the x, multiply by w1, add b, then go forward, so on and so forth, till we reach y. The moment we find out the y cap, that is the y predicted. Now we have the ground truth for it, that is the actual y value. Then we calculate the loss. If it is a regression loss, we use MSC. There are multiple types of loss for it, like regression as well as classification. Another loss is, for example, like classification loss, let's say binary cross entropy. But these are the more basic losses. Other losses that you will see in your paper are either some form of MSC or some form of BC. There are other some variants, but majorly these two are like more popular variants. And some combination of this is used. Directly BC probably you will find rarely nowadays. Okay, so but now you found the loss. I understood that combination of this W1, W2 and W3, all of them together are responsible for my loss. Yes, it's not that the one loss, which was easy in linear regression, which was easy probably in others. But here three weights are responsible. And it's not three weights that are linear related, rather there is some non-linearity and there is some sequence of ordering. Yes. And I hope you remember the total forward pass. And so what we do is basically uh, instead of because we cannot do direct, so what we do is something called backpropagation. In backpropagation, we basically backpropagate the gradient. Gradient is basically let's say the derivative of the loss with respect to the let's say the input that we want to find out. We find out, but we cannot directly find out, so we use basically chain rule to come back. Yes. So if we want to find the derivative given a particular input x, yes, I got this loss. Now I want to find out who are all responsible, what should I change so that my law gradient will be minimum or the loss will be let's say minimum. So I want to find it like say loss with respect to x. So what I do is I follow basically the chain rule. Yes, I we have discussed chain rule earlier also. So instead of finding with x, what I find is the derivative of loss with respect to first y, the output y. Then I find out what what change what change in y, like how much how do I say uh, how much change in y causes how much change in loss, let's say. And then similarly, how much change in w3 causes how much change in the y, how much change in W2 causes how much change in W3, and how much change in W1 causes how much change in W2, and how much change in X causes W1. So instead of approaching from X to L directly, we go through like a chain rule. Yes. So we ask this question again and again. Yeah. Uh, I hope that relates to. I will try to add a like very nice video where it is like video will help you. It's a little bit difficult over online, but let me share back. Okay, fine. So we have found loss, then we end up with a backpropagation. Now, backpropagation, I told you, so we want to find out the gradients, and based on the gradients, we can update the weights. Yes. So what do we want? So we want to find out what change, how should I change my W so that my loss becomes less? So I have to find derivative of loss with respect to weight, derivative of loss with respect to like a bias. We have done this exact thing during gradient descent for linear regression, let's say, and that is applicable to most of the algorithms. Here, the goal is to find out for every layer what should how should the weight change in every layer so that my loss is minimum. Yes, because every layer weight was responsible for this particular loss. And if the loss is not if the weight are not immediate, we basically use intermediate chain rule to propagate. Yes, we discussed that through diagram. Yes, and if you see, there are like recursive relationship that exists. I told you like because it's like how do I say? Like if you want to find with respect to W, first you find with respect to the Z. Z is what is the pre-activation thing. And Z, if you know, Z1 is basically W multiplied by X plus the bias term is there. So eventually you will have such a kind of recursive relationship while calculating the derivative. Now, one of the examples here, for example, output layer is there. So if you have MSC loss and sigmoid output, let's say, you will have delta L, let's say we want to find out, and that will be like derivative L with respect to Z of like delta of ZL. So that becomes with the chain rule that becomes del L by del A into del A by del Z. And so del L by del A will be one value, and then del A by del Z will be another value. So these two values we keep, and then because sigma, then we have a like a sigma derivative of sigma, then because it is sigmoid, we will have its corresponding derivative. It could have been ReLU, we could have its corresponding derivative. So then what we end up with is a very simplified solution for sigmoid and MSC. And this is what we keep on doing for a lot of things. Sorry. And hidden layers also same. So once we reach to the hidden layers, again we do the same back propagation that keeps on happening. We keep on asking the question how on in every layer what should be the change of the weights so that my loss reduces. Yes. Uh, and the same formula propagates. Yes, this is the in forward pass from x we go to y, in backward pass we from y we go to basically x. So basically errors flow back, so that is called, that's why back propagation. Yes. Weight gradients are calculated, bias gradients are calculated. Again, you need to make sure the dimensions are matching. Yeah. There is a small example. If you have input that is 3 hidden neuron and then output, you have an input, then you have 3 hidden neurons, and then you have output of 1 neuron. Forward pass is very simple. Z is equal to Wx plus P. We apply the first layer. A1 will be sigma of Z1. Then Z2 is equal to W2 A1 B2. And then Y cap we directly predict applying nonlinearity over Z2. Okay. Now then we calculate the loss. So loss will be, let's say, MSC loss here. So we have found half of like predicted minus actual whole square. Now what happens in backward pass? Now that we have found the loss, we do the derivative of that, and then we have like derivative of like of Z2. That is the second layer derivative, and then for the first layer we have multiplied W2 delta 2 and then again sigma Z of Z1. And then for each of these derivative, we have separate equations, and then we find out, and then finally this backward pass. Yes. So what is the total, finally, all things that we do? So every layer's new weights basically becomes, so we start with random weights, and now the new weights on every layer will become this. Yes. And it once we find the derivative, I hope you remember in gradient descent, we don't really subtract the, or let's say uh, move in the opposite direction with the whole value. Rather, we use something called a learning rate. So we don't move, let's say the gradient was, let's say, -5. We don't move by -5. Rather, we move by learning rate multiplied by -5. So the same principle, WL is equal to WL minus eta of, like, what is the gradient of L with respect to W. And similarly, BL is BL minus learning rate multiplied by like gradient of L with respect to BL. So like we have forward pass for predictions and loss calculation, backward pass for computing gradients by backpropagation. Then we update, we adjust the parameters using gradient descent, and we repeat until convergence or max iterations. And we have a learning rate eta, let's say, which controls the step size in parameter space. There are few things though that just why, and backpropagation definitely works because we compute like we can naively compute which weights exactly are responsible. Uh, but then the point is this one, if we do this partial derivative independently, we end up with, let's say, like m parameters n neurons, we'll end up with time complexity mn square. It's like we can have really large networks with multiple layers and each layer having a multiple number of neurons. Yes. But in backpropagation, what we can use is basically use chain rule. Yes, time complexity is very small, and it is also very super memory efficient. Yes, we can use Jani program to solve gradient computation, and like polynomial time, we can solve this. And a few derivatives of the existing activation functions, we have discussed this anyways. ReLU is super simple, 1 or 0, and so on and so forth. Yes, and then summary is there, class 2 key concepts. But the only thing I wanted to say, like backpropagation, it works really nice, but there is a different way, a lot of different libraries approach it. We will talk if there is time on it. So what we discussed today, we discussed how multiple layers solve XOR problem and other nonlinear problems. There exists a universal approximation theorem that basically theoretically grounds, okay, doesn't, if you take one hidden layer also, you can solve any problem. And then forward propagation is there. We basically keep on doing matrix multiplications of weight and like the input, and then the hidden representations plus the bias and then nonlinearity. And otherwise, then we can also go from the back propagation, right? So we calculate using gradient computation using chain rule, and then we just propagate the gradients back. Yes. Uh, that's all for today, basically, backpropagation, forward propagation, MLP architecture. The only caveat I just want to say, because just so that you don't take away super wrong thing here. Generally, when we calculate this backpropagation, if you are using some libraries for this one, and remember we used sklearn For the classical, like the machine learning that we did before this perceptron class, we'll be using other libraries to solve our deep learning task of multi-layer neural networks. All these libraries, for one of the examples, let's say PyTorch, they do something really nice stuff. Not specifically, they don't, they calculate this one, but they don't do like a chain rule explicitly. Now, what do they do is basically they store the gradients at each position, and they like there is brilliant maths behind it. It's easy to understand. It's not that super complex to hard, but if you want to look at it, you hopefully if you have time over the weekend, uh, you can look at something called a PyTorch AutoGrad. Fine. Brilliant maths that will tell you like exactly how we store the gradient. Yes, that is what basically pushes like how fast this back propagation can be done. Because as you understand, like because there can be many neurons in each layer and it can be many layers, this becomes extremely hard, right? It becomes extremely difficult to also like the number of neurons and everything else also increases. M into N still is very high. But we can do even faster using like let's say PyTorch and other. Yeah. So yes, so that's it for today. I can show you the code for that will give you a little bit more influence, but like we are around 5:30 already, so I will leave you to it. So and Monday is Deepavali, so we have no class. Next we will meet on Wednesday 4:30. Yeah. Okay, so if I take the next class, then we'll go through the code of, let's say, multi-layer perceptron. We will have more idea. Those who could not understand or feel everything, when I show you the code and maybe a little bit more graphs, maybe that will come a little bit more to reality. But otherwise, please go through the slides and notebooks. Yes. Okay, are there any questions? I will wait for like 1 minute. Otherwise, we will meet on like 4:30 next Wednesday. No class on Monday, Deepavali. The current side, yeah, sorry, Varun. So the slides I basically uploaded, yes, yes. So on this slides I was updating for today's, I just uploaded in a hush, but I will update it now so that it looks as good as we went through. Yeah, yeah. Thanks, Varun. Yeah. Any other questions? Okay, like happy Diwali to all. So please enjoy as much as possible. If you have some time, please go through this one. This is very interesting as such. Like MLP is where last 15 years of research is. Technically, whatever papers you are reading, eventually we will start using all of these. So it's best if you understand all these pretty well. Yeah. Okay, fine. I will see you on Wednesday, next Wednesday, 4:30. Either me or Professor Singh will be taking the class. Okay, bye all. Yeah. Sunny, happy Diwali to you also.